Here I am testing a model boat in seawater. Notice that it doesn't have any propeller, but neither does it have any duct or channel that you would typically find on magnetohydrodynamic boats. To appreciate what's going on here, I'm going to do a comparison with more conventional designs that use ducted flow. This is the Yamato one, a 30-meter research ship that was built in Japan in the early 90s. It had two magnetohydrodynamic thrusters, each housed in a pod underneath the main hull. Another interesting example is this 50 centimeter Catamaran model. I found this in a journal article called The Experimental and Theoretical Study of Magnetohydrodynamic Ship Models. The great thing about this was that if I built something to similar scale, I would have a direct comparison with which to evaluate my performance. Two fundamental design changes that I had in mind, namely the thruster and the hull shape. I will dive into the details a little bit later, but just in brief, I had a feeling that thrust could be generated more efficiently than by using a ducted thruster. I was also convinced that the Catamaran hull shape was far from optimum and that a radical different hull shape is called for. The research team simply proclaimed the Catamaran design as the optimum choice right from the start. I spent a considerable amount of time comparing the resistance graphs of different hull shapes on a small program called Michelet. I also modeled the Catamaran as well as the Yamato 1 hull using Michelet, and I will compare the results later. I selected the most promising hull shape and built a model out of polystyrene covered in fiberglass. Small amounts of carbon fiber were added where necessary. I didn't do any calculations or analysis on the magnetic and electrical side of my thruster. I simply chose magnets of roughly equal volume to that of the Catamaran design. I investigated the shape of the external magnetic field and used that to guide me in shaping and placing my electrodes. Now for some speed tests and results. The Catamaran achieved 82 mm per second in seawater and using a 3-cell LiPo battery. It drew 93 watts. They achieved 130 mm a second with a 6-cell LiPo battery, generating 382 watts. My aim was to better that speed on the same amount of power or less. At similar voltages, my boat produced 50 watts and 200 watts respectively. These lower powers are simply because of the orientation and wide spacing between my electrodes. These two curves are simply the displacement measured against time using a 3-cell battery. And here are the same results compared to the Catamaran results in blue. The orange curve is the results of my boat with a 6-cell battery. Unfortunately, the Catamaran did not publish their results for 6 cells aside from their top speed. It looks like the Catamaran had a very unsteady start, probably due to some sloshing in their test tank. I've fitted polynomial trend lines to these displacement results, so to get velocity and acceleration, all I had to do was take the time derivative of the resulting polynomials. These curves are only approximations, but they do paint a very good picture of what's going on. The Catamaran was tested over a fair distance, so I've included some of the extended results, which show how the speed creeps up to the top speed of 82 mm a second. The derived top speed for my boat is around 95 mm per second. This was confirmed by analyzing the video footage, where the boat consistently covered between 90 and 100 mm during the last second of each run. The top speed with 6 cells is 140 mm per second. This is the acceleration plotted against time. The drag at the start of each run is practically zero, so the initial acceleration is directly proportional to the thrust, which can be calculated using Newton's second law. The result is a staggeringly low 19 millinewtons, or roughly 2 grams of thrust. The jerky start of the Catamaran made any attempt of calculating initial acceleration or thrust impossible. If I look at the original displacement data, it looks like the Cat actually got off the mark slightly quicker. Another thing that is apparent from the acceleration graph is that the acceleration with the 6-cell battery, the orange curve, is roughly double that of the acceleration with only half that voltage. That is to be expected because double the voltage would mean double the current through the water, and since thrust is proportional to the current, that would also give double the thrust, hence double the acceleration. My boat still clearly carried a lot of acceleration at the very end of the run, which indicates that it is capable of still higher speeds. Measuring true top speed would require a lot of space for the boat to accelerate. I tried to do this on open water, but the wind, the current, and the waves made things very difficult. The best I could do was to measure the time it took the hull to cover its own length, using flotsam on the surface as a reference. Or to measure the time it took the shadow of the hull to slide over a fixed point on the bottom. Results varied, but a number of readings came in at between 150 and 165 millimeters per second. That is practically double the speed of the Catamaran, on barely more than half the power. I never managed to get a proper top speed reading on open water using the higher voltage. However, just looking at the results from the container, the fact that the hull achieved higher speeds in such a short distance than the top speed achieved by the Catamaran shows that one or both those modifications that were made paid off in spades.